Hello everyone, how are you all doing? I hope all of you are doing good. So welcome to Memoneet. I am Aprajita, your chemistry SME, and I welcome you all to today's another amazing lecture. So students, before starting today's session, I want to tell you that we have started the lectures for BPT4, that is your Bhramastra part test 4, that is going to be held on 23rd of June, right? So I hope all of you have started preparing for it. Yes, that's great. So there are going to be two chapters that are asked in your BPT4 from chemistry. I am saying that is structure of atom and chemical bonding and molecular structure. So first of all, I have started with structure of atom and I have posted the first video lecture, that is structure of atom part 1 on YouTube. Okay, in the chemistry playlist, you can go and watch that if you have not watched it yet. Okay, so go and watch that and then come back and see this lecture. Okay. So this is your part 2. Now let me tell you what I have covered in part 1. So in part 1 it was a kind of introduction where we talked about the subatomic particles. We saw the discovery of electrons, how they were discovered using the cathode ray tube experiment. We discussed about the discovery of protons and neutrons as well, then their characteristics, and after that students we studied the various atomic models, right? We studied two models, that is the Thomson's atomic model and the Rutherford's atomic model. So Rutherford, how he did that alpha particle scattering experiment, and after that what were the results obtained from that and what were the conclusions made out of it, right? So we left at the point where we discussed the limitations of Rutherford's model. Can you recall the limitations of Rutherford's model? That it could not talk about the stability of the atom and it did not talk about the arrangement of electrons around the nucleus. Right. So I told you after that we will be discussing another model, that is the Bohr's atomic model. So Bohr's atomic model we are going to learn today, but before learning about Bohr's atomic model, we need to see what were the developments that led to the evolution or discovery of this Bohr's atomic model. So various researches, various studies were carried out. So the interaction of radiations, right? Interactions of radiations with matter, actually it gave us a good idea about the structures of atoms and molecules. So what Bohr did, he used these results only to have his own atomic model. Based on that, he gave this to it, this atomic model. So there were these two things, students, two main things that he kept in mind, that is the dual character of the electromagnetic radiation. Okay, EM radiation means electromagnetic radiation. Dual character means the particle like nature and the wave like nature as well. Okay, and the second one is the experimental results obtained from the atomic spectra. So both of these we are going to discuss today, dual character of electromagnetic radiation and the atomic spectra, which led to the discovery of Bohr's atomic model. Okay, so first of all let us start with the dual character of electromagnetic radiation. Dual character means the radiations, they possesses wave like nature and particle like nature as well. So what we will be discussing first is the wave like nature. Okay, so what do we mean by wave like nature of the radiations? Let us start. So light, or you can say that in electromagnetic radiations, they possess wave nature as well as particle nature. If I talk about wave nature, students, so actually there was a scientist whose name was James Maxwell. So you might study it in physics as well, the Maxwell theory. Okay, so he was the first one who actually talked about the interaction between the charged bodies and the behavior of electric and magnetic fields on macroscopic level. This we are studying at microscopic level also. Okay, so he first talked about it at macroscopic level. So he actually suggested whenever we are having electrically charged particle and it is moving under acceleration, so alternating electric and magnetic field will be produced and transmitted. Okay, so with this we studied yesterday also, na? So students, basically what is happening in this case, if you are having any electrically charged particle and it is moving under acceleration, just like we have our electrons, remember, these are charged particles and they are moving under acceleration around the nucleus. So when it is happening, so by that motion electric and magnetic field will be produced by that motion only, and that will be transmitted. So वो जो electric and magnetic field है, they will be transmitted in the form of waves. So those waves are called as electromagnetic radiations or electromagnetic waves. So the name itself is explanatory, na, self-explanatory. Electromagnetic means the one having electric and the magnetic field as well. Okay, so actually Maxwell was only the first one who suggested कि light waves, okay, or light, they are also associated with your oscillating electric and magnetic field. Now you can see in an electromagnetic wave, here you can see this is the direction of propagation of wave. So this is the electric field, the orange one, and the blue one is magnetic field. Okay, so now the oscillating electric and magnetic field जो यहाँ पर produce हो रहे हैं, these are perpendicular to each other. You can see they are perpendicular at 90 degree to each other, as well as class they will be perpendicular to the direction of propagation of wave, right? Means this, like this. So here it's the direction of propagation of wave, here it's the electric field, here is the magnetic field. So they are perpendicular to each other as well as to the direction of propagation of wave. So that is about the electromagnetic wave. So we need to know a little bit properties of electromagnetic wave. Now basically what we are studying, let me recall you, we are studying the developments that led to the Bohr's atomic model. So this was not studied by Bohr, okay? This is a theory given by Maxwell. So we are studying the wave nature of electromagnetic waves, then we will study the particle nature, okay? Then we will study the spectra. So all these things then combined led to the development of Bohr's model. That's our main focus, okay? So this is just a little bit idea, but you have to know about the electromagnetic waves, all right? Now class, unlike sound waves or water waves, these electromagnetic waves, they do not require any medium, okay? So electromagnetic waves jo hain, they can move in vacuum as well. They do not require any medium for propagation, unlike your sound waves or water waves. Okay. And yes, there are many types of electromagnetic waves or radiations which differ in terms of wavelength or frequency, and they constitute the electromagnetic spectrum. Now, what is that electromagnetic spectrum? Let me show you. So here you can see, students, this is your electromagnetic spectrum. But before that, you must know what is wavelength and frequency. Okay. So wavelength and frequency are actually the characteristics of your waves. Okay. Now, what do you mean by frequency? So what is frequency, students? It is the number of waves that are passing through any point. Okay, like we take a point, so number of waves passing through a point in 1 second. कि 1 second में how many waves are passing through that particular point is known as the frequency of that wave. It is denoted by a symbol nu. Okay, and the units are hertz. So the SI unit is hertz, which we use for frequency. Okay, so you can see that how much waves are passing through a point in 1 second, that will be known as the frequency of the wave. And if I talk about the wavelength, so wavelength is, the name itself is explanatory, na, the length of the wave, right? So wavelength means distance traveled by the wave in one oscillation. Okay, in one complete oscillation, how much distance is traveled by the wave, that is called wavelength. Means it can be a distance between two corresponding crest, one crest and one trough, okay, or two corresponding troughs. So that is wavelength. अब its wavelength, तो इसके SI unit क्या रहेंगे? SI unit will be the unit of length only, which is meter. But since the wavelength of EM waves are very small, so हम small units लेते हैं, like nanometer and all of that. Okay, and the wavelength is denoted by lambda. Okay, so this is the symbol that we are using for the wavelength. So now that you have understood frequency and wavelength, I want to tell you one more thing, that these electromagnetic radiations in vacuum, they travel with the speed of light. Okay. So what is speed of light? Speed of light is denoted by c, which is 3 into 10 to the power 8 meter per second. So these electromagnetic waves, they travel with this speed of light. Okay. And there is a relation between the speed of light, c is equal to nu lambda. Okay, so this is a very important relation, keep that in mind. C is equal to nu lambda means frequency into the wavelength. Okay, so c is your speed of light, 3 into 10 to the power 8 meter per second. Then there is one more property of your wave that we use, that is wave number. Okay, now wave number is also sometimes used to represent the wave. So students, it is actually the number of wavelengths per unit length. Okay, so that is called the wave number, and the units or the representation is nu bar. So that is the representation of wave number. So now you see this electromagnetic spectrum. Let me explain you a little bit. Okay, students. So here you can see that the frequency is decreasing in this case. Okay, decreasing frequency is there. Okay, and increasing wavelength. Okay, so here you can see the wavelength is increasing. So gamma rays are the one that are having the highest frequency and lowest wavelength, followed by X rays, followed by UV rays. Then students, we have this visible spectrum. So this is the light only that we can see. Okay, only the visible light. Other lights we cannot see, other radiations we cannot see. So here you can see the wavelength is from 400 to 750 nanometer. Okay, so nanometer, you know na, 10 to the power minus 9 meters. So the purple light is there having the lowest wavelength, red light is having the highest wavelength, means the lowest frequency. Then we have the IR radiations, infrared, microwave. Then we have radio waves that are used in radio signals, and then long radio waves. So this is your electromagnetic spectrum, in which there are the radiations of different frequency and wavelength. Okay, so class, that was a quick idea about the wave nature of electromagnetic radiation. Now we will be seeing the particle nature of the electromagnetic radiation. Okay, so if I talk about the particle nature of electromagnetic radiation, so actually it was given by Planck, okay, Max Planck. So we call it as Planck's quantum theory. So basically students, what happened is, by the wave theory that your Maxwell gave, so it could explain certain phenomena like diffraction, which is the bending of light around an obstacle, interference, which is the combination of two light waves, right? So it could be explained on the wave nature, right? But there were certain observations that could not, certain effects that could not be explained on the basis of the wave theory. Okay, so what were those effects? Those effects were nature of emission of radiation from hot bodies like black body radiation. It could not explain the photoelectric effect, variation of heat capacity as a function of temperature, and line spectra of atoms, especially for the hydrogen. So what are these things? We'll be seeing black body radiation and photoelectric effect first. So students, you know actually what is black body radiation. So you know solids, when you heat solids, they emit radiations, right? For example, let's say if I am heating an iron rod, so what happens when you heat an iron rod in a furnace? Have you ever observed someone heating an iron rod? So firstly it gets red in color, right? Then if you heat it, if you increase the temperature, it increases, right? The redness increases, means it becomes bright red. Then slowly it will become white. Okay, then from white it will become blue if you are heating it at a high temperature. So what is happening? This color change is happening from a lower frequency region to higher frequency region, because you know that red color has low frequency and the blue color has high frequency. Just now we have seen, no, from the electromagnetic spectra. Let me show you again, like here. So red color will be having more wavelength, means low frequency, and the blue color will have high frequency. Okay, so actually the radiations are coming out from low frequency to high frequency as the temperature is increasing. Okay, not just in the case of iron rod, it happens in many cases, like from when you are heating the solid, the color changes from red to blue. Okay, so an ideal body, now what is a black body? An ideal body which can emit and absorb radiations of all frequencies, okay, is called black body, and the radiations emitted by such bodies are called the black body radiation. Now this phenomena could not be explained on the wave theory, okay, the wave nature of your electromagnetic radiations. So from here what we can say कि जो variation of frequency है, that is depending on temperature, because temperature के साथ the color is changing ना, and the frequency is changing. So what it is found that at a given temperature, the intensity of radiation hai, means the intensity at which the radiation is coming out, it increases with an increase in wavelength of the radiation. So that firstly increases to a maximum value, then decreases with an increase in wavelength. Okay, तो पहले जब wavelength बढ़ेगी, intensity of radiation बढ़ती जाएगी up to a particular value. अगर फिर हम जो आपकी वेवलेंथ फर्दर बढ़ा दें, राइट, सो इन दैट केस जो इंटेंसिटी है वो कम हो जाएगी. बट दिस फिनोमेना कुड नॉट बी एक्सप्लेन्ड विद द हेल्प ऑफ मैक्सवेल सजेशन, मीन्स द वेव थियरी. सो प्लैंक, ओके, मैक्स प्लैंक वाज द साइंटिस्ट हु प्रपोज्ड प्लैंक्स क्वांटम थ्योरी टू एक्सप्लेन दिस फिनोमेना. नाउ व्हाट इज दिस क्वांटम? That's what we have to see. So students, Planck actually suggested that the atoms and the molecules, they could emit or absorb energy only in discrete quantities, okay, not in a continuous manner. Like we saw na the wave nature, so it's in continuous manner. So that's in continuous manner, but Planck suggested that atoms and molecules, although they will emit energy, but only in discrete packets. Discrete means that is not continuous, okay, in small packets like that, okay, not continuous. And these small packets were called quantum. Okay, so quantum is actually the smallest quantity of energy that could be emitted or absorbed in the form of electromagnetic radiation. So quantum is actually the smallest unit of energy. That's what he said. Okay, so he said that the energy of the quantum of a radiation will be directly proportional to the wavelength. Okay, sorry, wavelength nahi, directly proportional to the frequency. So sorry. So if we remove this proportionality sign, we get a proportionality constant, which is h. Now this h is known as Planck's constant, and the value of h is 6.626 into 10 to the power minus 34 joule second. Okay, so the energy will be directly proportional to the frequency. That's what he said. Okay, so that's the Planck's equation, you can note. And with his theory, Planck was able to explain the distribution of intensity in the black body as a function of frequency or wavelength. We saw na कि when the wavelength is increasing, first the intensity increases up to a maximum value. Then if we further increase the wavelength, the intensity of the radiation will decrease. So Planck could explain this. Here you can see that the intensity or the energy is dependent on the frequency, or the if it is dependent on frequency, indirectly it will be dependent on the wavelength only. So that could be explained here by the Planck's theory. Okay, so he was able to explain the black body radiation. Now the second point was ejection of electrons from metal surface when radiation strike it. That is the photoelectric effect. Now let's see what is the photoelectric effect. So let's see photoelectric effect, students. So actually H. Hertz performed an experiment, okay, in which he fired a beam of light, okay, to a piece of metal. All right. So what happened is that a beam of electrons were noticed, okay, or they were ejected when the piece of metal like potassium, rubidium, cesium, they were exposed to some light. Okay, so this is called a photoelectric effect. That is, it's actually a phenomena in which electrons are ejected from the surface of metal when light is incident on it. Okay, and these are called as photoelectric electrons. Okay students, so this process is also called as photoemission. Now what is happening in this case, the photoelectric effect is happening because the electrons that are present in the surface of metal, they actually absorb the energy from incident light. Okay, they absorb energy from the incident light, they overcome the attractive forces that bind them together, and they come out. Okay, they get ejected. Now what were the observations that were made out of this photoelectric effect? So electrons जो है, they are ejected from the metal surface as soon as the beam of light strikes it. मतलब there would be no time lag or no time gap in between. So as soon as light strikes the metal, electrons would be ejected. Now a very important point class, that is the number of electrons is proportional to the intensity or brightness of light. Okay, लाइट यू आर लाइक पुटिंग ऑन द मेटल, सो जितनी ज्यादा इंटेंसिटी होगी, जितनी ज्यादा ब्राइटनेस होगी, द नंबर ऑफ इलेक्ट्रॉन्स वुड बी more. Okay, so although the number of electrons actually depend on the brightness of light, up the energy by which the electrons are emitted or ejected, that does not depend. Let me tell. So it's not like that ki you will put any light and the electrons would be ejected from the metal. No, for each metal there is a characteristic minimum frequency which we call as nu naught. Okay, इतनी frequency की light अगर हम डालेंगे इससे ऊपर की frequency की, then the photoelectric effect would be observed. If the frequency of light is less than the nu naught, which is the threshold frequency, no photoelectric effect would be observed. Okay, so what is happening in this case, if we are taking any frequency which is greater than nu naught, so जो electrons हैं, they will come out with certain kinetic energy. So जो kinetic energy होगी, that will increase with the frequency of the light used, not with the intensity of light. Students, kinetic energy actually it depends on the frequency of the light used, not on the intensity. Okay, but according to your classical theory or the wave nature, the intensity, like the intensity of light that we are putting on the metal actually, so उसका जो energy content है, that depends on the brightness of light only. So according to that theory, जो number of electrons है and जो kinetic energy है, वो दोनों brightness of light पे depend करनी चाहिए. Although the number of electrons depend on brightness of light, but kinetic energy जो है वो brightness of light पे depend नहीं कर रही है. So this thing could not be explained by your wave nature. Okay, so Einstein actually used the Planck quantum theory to explain this effect in such a way. Here we can see. So Einstein actually said कि जब हम light beam fire कर रहे हैं और we are shooting a beam of light on the metal, so it can be seen as the beam of particles. Okay, beam of particles which he called as photons. It's not a continuous light beam. It's like some packets of particles, that is the photons, are striking the metal surface. So when the photons of enough energy, they strike the metal surface, they transfer their energy to the electrons. Okay, so the photons ki energy thi, that will get transferred to the electrons and they will get ejected as soon as that photon strikes the metal surface. That's why there is no time lag. Okay, so let's say if the energy of the photon, it's h nu. Okay, and this is h nu, and you know minimum frequency required is nu naught. So the threshold energy means the minimum energy required to eject the electron is h nu naught. So jitni energy bachegi, the energy that would be left will be the kinetic energy by which the electrons would be ejected. So h nu minus h nu naught, or you can say that h nu is equal to h nu naught plus kinetic energy, which is half mv square. You know na kinetic energy. So this is the relation for the ejection of electrons. Okay, इसको हम work function भी बोलते हैं. This is also known as work function. Means how much minimum energy is required to eject the electrons. So actually what did we see here is that the light beam can be seen as a packet of particles, like a particle striking the like the metal, and those particles are known as photons, which transfer their energy to the electrons and they get ejected. Okay, and you can see now that the kinetic energy will be dependent on the frequency. That's what we have seen. So see, ये point यहाँ पर explain हो गया कि how the kinetic energy depends on the frequency. So this is how, students, the particle nature of light could be used to explain the black body radiation as well as the photoelectric effect. Okay. So now, students, we will be seeing the line spectra of hydrogen. But before that, I want to tell you a little bit about the continuous spectrum, emission and absorption spectrum. So you know that when light goes from one medium to another medium, it gets refracted. You have studied the refraction of light, right? And you have studied when a light passes through prism, so it splits up into 7 colors, right? So red light is deviated the least and violet light gets deviated the most because it has the least wavelength, and you see a spectrum where all lights merge into each other. So this is known as a continuous spectrum. You can see here violet merges into blue, blue merges into green, then yellow, then red. So it's a continuous spectrum, right? So then what is the emission and absorption spectrum? So in this case, the spectrum of that radiation which has been absorbed, like which has absorbed a certain amount of energy or certain radiation, is known as emission spectrum, as you can see here, students. Okay, and absorption spectrum is actually like a photographic negative of the emission spectrum. The radiation that has been absorbed, there you will get a black line. Here you can see black lines. So that's actually kind of a photographic negative for the emission spectrum. So when we study these light spectrums, that is the continuous, emission, absorption spectrum, the study is known as spectroscopy, and it's a very important branch of chemistry, okay, where we study these spectrums. Now if I talk about the emission spectrum in the case of gases, because now we are going to talk about hydrogen, which is a gas. So in the emission spectrum of the gas, students, what happens is, so for the gases, students, they do not actually show a continuous spread of wavelength, but they emit light at certain points only, at certain wavelengths only. Then we call it as a line spectrum or a line spectra. Okay. So in the case of gases, we do not get a continuous spectrum. We get the wavelengths at certain positions, which we call as a line spectra or an atomic spectra. So that's what we are going to study. That is the line spectra of hydrogen gas, which led to the development of your Bohr's atomic model. Okay. So students, if I talk about the line spectrum of hydrogen, so you know what happens actually is, whenever any electric discharge is passed through the gaseous hydrogen, we have the H2 molecules, right? These H2 molecules dissociate into hydrogen atoms, and these energetically excited hydrogen atoms, they emit electromagnetic radiations of discrete frequencies. Okay, discrete frequencies are there. So if we want to study these discrete frequencies, again we get this line spectra of hydrogen. So there was this Swedish spectroscopist Johannes Rydberg. He actually noted that all series of lines in the hydrogen spectrum could be described by this expression. So we get different lines in this case, and those lines were named after their discoverers. Okay. So the formula is represented like this, where this nu bar is the wave number. So we are representing the lines in the wave number. Okay. So 109677. Now what is this quantity? It is known as the Rydberg's constant. So you have to remember this number and you have to remember this formula also. So here 1 upon n1 square minus 1 upon n2 square. Okay. So now where n1 means the first energy level and the n2 is the higher one, the excited one. Okay. So here this is the line spectra of the hydrogen. Okay. So if I talk about n1, so n is equal to 1. So if n is equal to 1 means any electron is falling into the first shell here n equal to 1. So we get this Lyman series, and this Lyman series is not visible. Lies in the ultraviolet region. Then n equal to 2 clay, we have Balmer. So this is the only series which lies in the visible region. This you must know that Balmer series is the only series of lines which lie in the visible region, as you can see. Then n equal to 3 means Paschen, which is near infrared, and n equal to 4 is bracket, which is far infrared, and again n equal to 5 is Pfund, which is again far infrared. Okay, so this is the line spectrum of hydrogen. So where we have Lyman, Balmer, Paschen, bracket, and Pfund. These are named after their discoverers, corresponding to the value n equal to 1, 2, 3, 4, and 5, and so on. Okay, and you have to remember the formula in this case, and the ones that are lying in the visible region is the Balmer series. Okay, so that's the thing, students. So now, students, if I talk about Bohr's model for the hydrogen atom based on this line spectra, Bohr gave the model for the hydrogen atom. So he actually said that the electrons that are present in the hydrogen atom, they can move around the nucleus in circular paths of fixed radius and energy. So remember Rutherford's model, he said that the electrons revolve in circular path, but he did not talk about the radius energy. Okay, so Bohr said that they are moving in a circular path, but that will be having a fixed radius as well as a fixed energy. And these paths were known as orbits, or he called them as stationary states or allowed energy states. Okay, and they are arranged concentrically around the nucleus. Concentrically means like this. If this is the nucleus, so like this, concentrically these orbits are arranged. Okay, the very important point that Rutherford could not explain is, he said that energy of electron in the orbit will not change with time. Okay, if it is revolving in a fixed orbit, it will remain like it will be having the same energy. It will not change with time. However, if the electron is moving from a lower state to a higher state, energy will be absorbed. Okay, and when it is moving from a higher state to a lower state, energy would be released, right? So that does not take place in a continuous manner, but again that takes place in a discrete manner. Okay, so how much energy is absorbed or emitted, that was also given by Bohr. Let's say if we have two energy states, electron is moving E1 in E2, two energy states are there. So what is E, delta E? It would be E2 minus E1, and you know that it is equal to h nu, right? The energy is equal to h nu. That's what we have studied from the Planck's quantum theory, right, students? So in this case, the frequency that we can find out would be the frequency of the radiation that is emitted or absorbed. We can find it out like this between the two energy states. So it will be E2 upon E1, sorry, E2 minus E1 upon H. So this is how we can find out the frequency of the radiation emitted or absorbed in this case. Okay, so you know about linear momentum, right? It's the product of mass into velocity. Just like we have angular momentum, which is the product of moment of inertia into angular velocity. This is actually a concept of physics. Okay, so the angular momentum is given by MeVr. Me means we are talking about electrons. So according to Bohr, students, the angular momentum is actually an integral multiple of h upon 2 pi. From this equation, we get to know that the electrons can revolve only in those orbits where the angular momentum is the integral multiple of h upon 2 pi. That means that only certain special orbits are allowed. It's not random. Electrons will not be randomly moving in any orbit, but according to this rule where the angular momentum is integral multiple of h upon 2 pi, right? So these are all the points from the Bohr's model that we are discussing. So you know that the orbits he numbered as n equal to 1, 2, 3, right? Like we call as K, L, M shells. Okay, according to Bohr, that's what he said, ki electrons will be revolving in these orbits only. All right, then he said that the energy, now energy is very important, right? The energy that is associated with these orbits would be given by So that is students minus RH into 1 upon n square. So you see it is inversely proportional to n square, where RH is Rydberg's constant 2.18 into 10 to the power minus 18 joule. And using this we can find out the value of energy of every orbit, right? By putting the value of n like 1, 2, 3 and so on, we can find out the energies, and we see these energies are quantized. Okay, these have separate discrete values. So students, not just for hydrogen, this is valid for the ions having one electron. Okay, means the hydrogen like ions that we have, for example Li positive. Okay, then we have this lithium positive is there, 2 positive would be there, then He positive would be there. Okay, beryllium 3 positive is there, so they are having all one electron. So in this case the energy will be given by minus RH, okay, into Z square upon n square, where Z will be the atomic number, joules. Okay, so we will be using this formula to calculate the energy for the hydrogen like species having one electron only. Okay. So in this case, students, using the Bohr's atomic model, we can explain the line spectra of hydrogen. That is, radiation will be absorbed if the electron is moving from a lower principal quantum number to higher principal quantum number, and emission will be evolved, means radiation will be evolved when the electron is moving from higher principal quantum number to lower principal quantum number. In that case, the energy would be released. Okay, so that is what the Bohr's atomic model is. All right. Although Bohr's model was a like modified version of the Rutherford's atomic model, but there were certain limitations, students, that it was valid for only hydrogen atom or hydrogen like species like He positive, Li2 positive and so on. Okay, and it could not explain the splitting of these lines. Okay, so here we are not talking about splitting, we are seeing single lines only in the hydrogen spectra, but these lines they split into doublet. Okay, whenever we have this electric or magnetic field, so it could not explain the splitting of light in the presence of electric and magnetic field, which we call as the Siemens effect and the Stark's effect. Okay, the splitting of line, this Bohr's model could not explain, and it also could not explain the ability of an atom to form chemical bonds. Okay, so that is why we can say this model is fine, but it is valid only for hydrogen or hydrogen like species. It is not valid for the higher atoms. Okay, so then what after that? We have studied this thing, right? After that we will go on and we will study the quantum mechanical model. Okay, so we will be studying the quantum mechanical model of the atom in the next lecture. So for today we studied the various developments that led to the Bohr's atomic model, all right, and then we saw the Bohr's atomic model for the hydrogen atom. All right, students, but again it had certain limitations. So we will be studying the quantum mechanical model in the next class. So until then, students, take care of yourselves. Thank you. Bye-bye.